Graph in general can be defined as a collection of vertices V or a collection of edges E given in pair as U, V. This graph shows us both the representation with V showing all the vertices of the graph 0, 1, 2, 3 and E showing the edges formed between the vertices of the graph between 0 to 1, 0 to 2, 0 to 3 and 1 to 2. Adjacent matrix is a representation of using matrices of size n cross n, where n is the number of nodes in the graph. Let us take an example of graph with 4 nodes so that we'll have n as 4 and we obtain a 4 cross 4 matrix. At location r, ce, that is the rth row and the cth column, we represent in the matrix if it has an edge between those two or not. If the two nodes are adjacent to each other, that is, directly connected to one another without any other node in between, we represent that cell as 1, and if there is no edge or no adjacent, then we represent it as 0. Here we can see that 1 is connected to 2, 3 and 4, so that we are giving 2, 3 and 4 to be 1. And when we take node 2, we can see node 2 is connected to 1. So we have 1 only at node corresponding to 1. Similarly, when we see for 3, we see that 3 is connected to 1 and 4. So in the matrix we have 1 from 1 corresponding to 1 and 4. And also if we see for the node 4, we see that it is connected to 1 and 3. Hence in the matrix we have a connection corresponding to 1 and 3. Here we can see that diagonal in the matrix is all 0 because we cannot have an edge between 1 and 1 itself, which is called as a self loop and not an edge. Now here we can make an important observation that when I have a undirected graph, we see that matrix is diagonally symmetrical as traveling from R to C or from C to R is the same. But if we consider the edge to be directed, traveling from R to C and traveling from C to R is completely different. Here we have 1 is adjacent to C does not mean that 2 is also adjacent to 1, which would happen only if the edge is undirected or bidirectional. Hence the matrix formed for directed graph would be unsymmetric. Taking an example for the directed graph, we have there is a connection from 1 going to 2 and 3. Hence from 1 we have 1 at 2 and 3 correspondingly. If we see the same for 2, we don't have any outgoing connections from 2. That's why I've represented all the zeros corresponding to 1, 2, 3 and 4. Similarly, when I see for 3, I see that there's an outgoing connection to 4. That's why for the third node 3, I have 1 at only corresponding to 4. Similarly, when I do the when I consider 4, I see that there is a outgoing watch to 1 and also C 3. That's why I have 1 corresponding to 1 and 3 1 1, and all others are given as 0 and 0. After this intro, let me explain and execute a simple C++ code for adjacent matrix and show the obtained graph. After that, let us explain the code that is provided to us with both cases of undirected and directed and minor and this is a very simple C++ program to represent the graph in terms of adjacency matrix. So here we can see that we have defined a class called graph with private members and public members. In the private member, we can see that we have defined a graph 2D array of size 10, 10. It can be anything as required. In the public, we can see we have defined a constructor graph with an input taking x, which is the number of vertices in our graph. Here we can see that a matrix, as we have already created a matrix 2D matrix here, we are initializing all the elements to be 0, which is done by row, first running row wise and then column wise, and assigning it to 0 so that the whole matrix is converted to 0. Then we define display adjacency matrix. This is used to print the whole matrix starting from row printing its column and repeating the same for all the rows correspondingly. This is the main code to display the 2D array. G of I, j represent the cell formed by ith row and the jth column in the matrix. This is to add an edge between x and y, which is I and j. To check the condition, if x or y is greater than n, we say that the vertices does not exist. Like if I have four vertices in a graph, and if the input given x and y is beyond 4, so that will show that vertex does not exist. Similarly, here I check if it is a self loop. If both I and j are the same, it means that it lies in the diagonal of the matrix form, so it shows that it is a self loop and no edge can exist from a point to itself. If both the condition are not violated, then we go on adding edge into the matrix. Here we will give as g of y comma x to be 1 and g of x comma y to be also 1. This is the case for an undirected graph, because as I mentioned, adjacency graph in undirected graph means that edge being from 1 to 2 is also same as edge being from 2 to 1. If we want to do it for the directed graph, we will remove g of x y. If we want to increase the number of vertex, here we are increasing the number of This is used to increase the number of vertex in the matrix representation, and after increasing the number of vertex, we are creating new rows and new edges in the already present matrix, and declaring all of the new row and the new column to be all 0. Similarly, when we want to remove the particular vertex, x is the number of the x represent the number of the vertex which needs to be removed. For example, 1, 2, 3 and 4 are the vertices. If I want to remove 2, then x would be 2 here. This is for checking if the input given is beyond the already available vertices, and if that is not violated, a while loop would run such that first this is to remove the particular column, so that all the elements are shifted left side after removing that vertex, and this is to remove the row such that when that vertex is removed, all the elements would be shifted one block upwards, and then n would be decreased. N represent my number of vertices in my matrix representation. This is the main code. Now first I am declaring a graph of 4 nodes basically, and add edge 0 to 1. I am adding an edge between 0 1, 0 2, 1 2, 2 3, and here I am displaying the my present matrix. After this is my first output. Then for the second output, I am increasing the number of vertex. Presently my number of vertices were 4 here. Now after increasing the number of vertex, that means my matrix obtained will be 5 cross 5, and I am adding an edge at 4, 1 and 4, 3 here. Remember, my matrix here runs from 0 to n minus 1, and again I am displaying the obtained matrix. After doing this, my third output would be remove the vertex 1. So after removing this vertex, I am displaying the adjacency matrix again. So let me compile and show this. Okay, so this is the obtained solution. You can see 0 to 1, there is an edge. This is the 0, 1, 2 and 3. Accordingly, 0, 1, 2 and 3. 0 to 1 means there is an edge between 0 and 1 here. This is 1, this would be 0, and this would be 1th position. Accordingly, 0, 2. So there is an 1, 0th row and second column. Next, 1, 2. That means first row, second column, and similarly 2, 3, second row, third column. So as we have already said, for an undirected graph, it would be symmetric, so that we can see that this matrix right here is symmetric. similar, and I've displayed this matrix. After adding an vertex, we can see that the matrix now is a 5 cross 5 matrix, and the new edges added are 4 comma 1, fourth row first column, 4 comma 3, fourth row third column. We have added 1 and 1, that representing that we have added an edge here. Also we can see that the matrix obtained is diagonally symmetric. Now we can see after removing an vertex 1, that means we have removed this vertex from here, this vertex 1 and vertex 1, so that we can see everything from here is shifted left, 1 left, and everything from here is shifted 1 upwards. So this is my new matrix obtained after removing the vertex. Let me start by explaining first for the undirected graph. This particular code is written for both directed and undirected graph, weighted or unweighted. So first, this is the class class. This is the constructor, destructor, to check if there is a edge between I comma j, to add an edge, to add an vertex, and this is to add the edge between I comma j with weight w. This is weight with the weight w. This is to remove an edge between I and j. Out degree represents the outgoing edge from that particular vertex, and in degree represent the incoming edges to that particular vertex, and output is to print my whole matrix. Now let me start with the constructor. Vertices is the number of vertex that I am considering. For example, if I have 1, 2, 3 and 4, so my n would be 4, representing that there are 4 vertices that I am considering. First, I'll give edge e, the number of edges to be 0, so that initially my graph doesn't have any edge connections. This is to create a 2D array of a particular size according to the number of vertices. First, after creating the 2D array, which is my matrix representation, first row wise and then correspondingly column wise, I am clearing the whole matrix to be no edge, so that my whole matrix now is 0 0. If I have a 4 cross 4 matrix, then all of the 4 cross 4 terms should be 0 first. This is to check that if it exists or not. This is the condition between to check whether my input I comma j is less than 1 or is more than n. So that it ensures that the vertex I am inputting is within the range of 1 and n, and also it checks if there is no edge, then it returns false, otherwise it returns true. This is to add an edge between I and j with weight w. If it's unweighted graph, then we would not have this term, and here it would be 1. So to input I comma j, first I am checking and condition input of I comma j to obey that it must be within 1 and n. So this is to check if it lies between 1 and n itself, and if it does, I'll at that particular cell in the matrix I comma j, ith row and jth column, I'll add 1 if it is an unweighted, or w if it is an weighted graph, and increment the value of e so that it shows that there is an edge added. This would be helpful for us when we are removing the number of edges, so that we'll know when all the edges are done removing. This is to remove the edge between I and j. This is again to check if it lies between 1 and n. That is, I and j representing the cell lies within the matrix or not. When it is satisfied, a of I comma j, ith row and jth column, this particular cell is made no edge, so the edge between it is removed. If it is 0, if it is 1 or w, then it is made to be 0, and e is decremented, showing that that particular edge is decremented. This is to represent out degree. That means if I have a connection, this would be helpful for us in directed graphs. If I have a connection going from 1 to 2, that means when I draw the matrix, corresponding to 0, the row corresponding to 0 would have a 1 or weight w at 1, showing that there is a connection going from 0 to 1. So this is again to check my condition that it lies between 1 and n, and when it does, I'm checking that particular column from 1 to n, and this is when a of I comma j is not equal to no edge. That means that there is an edge existing between that particular I and j. So I increase the sum. Sum shows the number of edges outflowing from out degree. Out degree basically is the count of edges going out of that particular vertex, and similarly in degree is the count of incoming edges to that particular vertex. So here again I'm checking the condition to be between 1 and n, and when it is satisfied, I check if it is not a no edge, that is I'm checking if there is an edge existing between it or not. So when it does, I'm incrementing the in degree value so that it shows the number of incoming edges at that particular vertex. This is to print my whole matrix, 2D array or my adjacency matrix that I have obtained. First I do it row wise, then all its column, and similarly the for loop runs for all the number of rows. So in the end I will get a n cross n matrix. This is the main program. This is first I'm adding element between 2 to 4. This is for undirected graph that I'm considering. So adding between 2 comma 4 also means that I'm adding 4 comma 2. 1 comma 3 also means from 3 comma 1. 2 comma 1 also means that 1 comma 2, and similarly for 1 4 and 3 2. And this is to print the whole graph. Now I'm deleting the edge formed between 3 and 1. So 3 and 1, you can see 3 and 1 is also same as 1 and 3. So this particular edge would be removed, and I'm again, after removing that, I'm printing the graph again here. And again after removing that edge between 3 and 1, I'm checking if there is an edge existing between 3 and 1. So this would print my boolean condition either true or false. Since we have deleted the edge between 3 and 1, then the output here would be false. And now I'm checking the degree of 2. So my 2, since this is an undirected graph, out degree and in degree here is considered only as out degree. So when I check the degree of 2, I can see that there is a connection 1, 2 and 3. So the degree of my graph at 2 would be 3 here. And again I'm printing all the edges of present in the graph. This is the main class representation, very similar. This is my this is to add the vertex between that particular I, j. Here I have given 1 since I am considering it to be an unweighted graph, and this is to delete the particular edge between I and j. And here we don't require weight to mention the weight, because anyway it would remove the edge with or without considering the weight. So this is the main the driver code to add and remove the edges. So here we can see this is the condition for a weighted. So there is an when I want to add an edge between I and j with weight w, in the matrix at jth column and ith row I'm adding w. And similarly here we can see that we are adding only at a of j comma I and not a of I comma j also, since this they have considered with respect to a directed graph actually. And similarly when I want to remove that particular edge, I'll check the condition if it lies between 1 and n, and similarly after that I'll delete the edge. So a of j comma I in the matrix will be made to no edge, that is it will be made to 0, and the edge between that will be removed. And my degree here, this is the main change from directed and undirected. If we want the same in directed, we would have separate in degree and out degree. But this being an undirected graph, sorry, I was wrong that this was directed. This being an undirected graph, I have only one called degree here. So let me start by explaining for adjacency matrix representation for a directed graph, weighted or unweighted. So this is the CPP file. Now I'm adding an edge between 2 comma 3. Remember, this being a directed graph, adding an edge between 2 comma 3 is not same as adding an edge between 4 comma 2. So these are the only 5 edges that I'm adding into the graph, and also the output matrix that I obtain would not be diagonally symmetric. So here when I take the output of it, these are the 5 edges that I would obtain in the output, and this would form my first matrix output, and this would be, and after deleting the edge between 1 comma 3, I'm again printing the whole matrix representation so that I can see that there is an edge removed between 1 comma 3. And since this being an directed graph, it does not bother anything, it doesn't have to bother anything with 3 comma 1. So now I'm checking if there is an edge between 3 comma 1. This is just to trick us, since 3 comma 1 was never defined here, because this was a directed graph, so the boolean for this would always be false. And I'm checking the in degree of 3. So in degree of 3 shows the incoming edges towards 3. If I for a moment, if I consider that this was not deleted, you can see that for 3 the in degree here with all these edges would be 1, because to 3 there is an edge coming from 1, so it would have printed in degree of 3 to be 1. But since I deleted that particular edge, in degree of 3 would be now 0, and out degree of 1, so out degree of 1 shows the number of edges going out of 1. So I'm again considering this to be not done. So here I can see that there are 1, 2, 2. Out degree of 1 would be 2, because there is a edge going from 1 to 3 and also from 1 to 4. And again, when I consider this case, that is the edge between 1 and 3 to be deleted, the out degree of 1 would be only 1, because the only edge going from 1 is from 1 to 4. And again, see how this is to print all the edges in my matrix representation, that is between 2 comma 4, 2 comma 1, 1 comma 4 and 4 comma 2. So this is the class declaration. This is to add the edge between I and j with weight 1. If it was a weighted graph, I would have defined that weight w also. And again, to delete the edge between I and j, this would be a repetition, but let me just explain in brief now. So this is my class declaration, and this is my constructor to define my empty adjacency matrix with all the term to be 0. I'm defining the number of vertices n, so that my 2D array would be n cross n 2D array, and using this I'm clearing all the elements of the matrix and making it 0. Now this is to check if at that I comma j there is an edge existing, and this is to add an edge again. So similarly, if it is weighted or unweighted, for, w for weighted and 1 if it was unweighted. So this is my I'm adding an edge here after checking the condition that the input I and j are within the bounds of 1 and n, and increasing e so that I'll have the count of how many edges I had added. And similarly, this is to delete that particular edge after checking the condition of I comma j to be within the bounds of 1 and n. So when this condition is satisfied, a of I comma j would be made no edge, so that it shows the edge between I and j was removed. This shows the out degree for my directed graph. So this has the count of how many edges are going out of that particular vertex, and in degree similarly shows how many edges are incoming to that particular edge. In I'll explain only out degree here. First I'm checking to be in the bounds of 1 and n, and if not I'll throw a bad output exception, and if it is not, then I'll check the column wise, and whenever I find a particular edge in that column, that means that there is an outgoing edge from that particular vertex, and I increase the sum. Sum here shows the number of outgoing edges from that particular vertex. So similarly for in degree, and this is the final to print my whole uh, 2D array or my adjacency matrix. First I do it for a row and it's all corresponding columns, and similarly for next all the rows.